Hello, hello. Well, big day. I don't know if this is going to take 10 minutes or 2 hours. It's going to be good no matter what. So our goals today are sketch any factorized polynomial. Maybe you got this skill already. We're just going to make sure you can do it for any polynomial. We're going to use the factor and remainder theorems. Wow, finally, to reduce polynomials to a factorized form. All right, and then once it's factorized, we should feel good about sketching it. So when you use synthetic division, you're basically factoring out a linear factor. So that's beautiful. Hopefully goes well today. Hey, technology. Yeah, we live in this, we have electricity now, we have heat, it's amazing. We have these calculators that do a lot for us. So while we learn all the algebra and geometry behind the scenes, our technology does a lot for us. Hey, we'll throw in inequalities at the very end. Certainly more of a HL topic that, wow, we've got all these ideas. The real world works in inequalities. You want to find out what's the least amount of gas you need to get your vehicle from here to the moon. You don't want to be exactly right. You want to kind of know at least. All right, here we go. All right, so we'll start with sketching. First thing you want to do when you're sketching is figure out the end behavior. So as x becomes large infinity, a large negative infinity, the first step is to determine the leading coefficient. And we don't care what the number is. All you're keeping track of is positive or negative. Okay. And then second of all, determine the degree of the polynomial. So it might be split up. You're going to have to take this plus that, but figure out, and all we're really interested is odd or even. Why? Well, if we come over here, got a little table for you. If you have a polynomial that has an odd degree and a positive leading coefficient, then you know it's going to exit here and it's going to exit here. One of the more famous odd degree leading coefficients is y equals x. Yeah, because the leading coefficient is 1, positive. The degree of that is 1. I think you can handle that. So what if it's negative? And then it's going to switch. And a very famous one there is y equals negative x. So you don't have to remember odd or even. You can remember maybe two functions. And those two functions would be maybe x and maybe something crazy like x squared. So if it's even and it's a positive exponent, we got that and that. And if it's negative a value, we know it opens down. So it's going to be that and that. So you certainly can remember y equals x squared and y equals negative x squared. If you kind of remember those, you have this table. It's not something that you have to draw on your neighbor's back before the big test. All right. So we have to determine the behavior of the x-intercepts. Behavior, well, if it goes through the x-intercept, no big deal, right? But we have to know if the graph is going to cross through the x-axis or if it's going to swoop and be tangent. All right, so here is a linear factor, x minus alpha. That means alpha is our root or our 0. And when the power is odd, to the first power, third power, fifth power, what's happening there is this factor, whatever x is, when it gets next to alpha, a little bit to the left, a little bit to the right, is it going to change signs or not? Well, of an odd power, it will. So it's either going to look something like whoop, or it's going to look like this. Now, Mr. Sayers, really, you had to do 2? Yeah, because it depends on if you're coming from below it or above it. You know, I just want to make sure I cover everything on this. Let's go a little thinner line. So if it's even, then the graph is like woohoo, and it's going to do something like that, or it's going to do something like that. So even 2, 4, 6, 8, stuff like that. All right. And so a little icing on the top of the cake, icing on the cake is go ahead and find where it crosses the y-intercept because it's such an easy thing to do. Just let z equal to 0 or x equal to 0 and find the y-intercept. So oh boy. So the y-intercept, not too sure why it likes to jump. So the y-intercept is going to be 0, p of 0. Okay. All right, so our first example, let's make sure we can see that. There we go. All right, are we going to be positive or negative? So we have kind of a 1x cubed here. We'll have a 1x squared here. We'll have a 2x, and we have a negative 2. So our leading coefficient is going, well, the whole thing is going to be negative 4x to the 6. That's going to be our leading term. So it tells us a lot of information. First of all, it is negative, and it is even. So negative, even. So right away, I know it's going to exit here and exit here. All right, so that's weird. You know, you just graph. I kind of do that. That's okay. List all the x-intercepts. Well, the x-intercepts are going to be 1/2, 5, and 9 by the zero product rule. So you just, oh, yep, they're all positive. So here's 1/2, here's 5, and here's 9. Yeah, maybe not totally to scale, but you know, we get the picture. So we get something like that. And then the power. So the exponent of 2x minus 1 is 1. We have 2 and we have 3. So odd, even, odd. So this is how I do it. Maybe. Do I go through it 1/2 or do I just swoop it? Since it's odd, I go through. And at 5, I got a curve somewhere. Do we care about where that is? No. Maybe they ask you about those local minimums and maximum. That's differential calculus. We're not doing that right now. We're just sketching. So since it's even, we swoop. And then maybe, wahoo, then we go down. That is really ugly, but it's beautiful sketch. A beautiful sketch. And so the y-intercept might be really nice to find. So that's going to happen at 0. If we plug in 0, we get negative 2 times negative 1 times negative 5 squared times negative 9 cubed. Should have thought about this. So big number. Is it positive or negative? Let's just make sure we're going to get a negative out of this. We're going to get a positive out of this, a negative and negative. That's going to be a positive. It's going to be negative. So perfect. It's right there. Notice I haven't marked the y-intercept because I'm not going to until I know what that y-intercept is. And then I'm going to put this number right here. And people are going to like, wow, that is perfectly spaced. All right. So let's try a quick example, one more example just to make sure we have it. We have x to the 30th here, we have x to the 1st, we have x squared, and we have positive 2. That's going to give us 2x to the 33rd. So we know the leading coefficient is positive, and we know this is odd. So I would expect this to go this way and this way. A positive odd graph. All right. X-intercepts are at 1/2, 5, and 9. 1/2, 5, and 9. So here we go. When we get to 1/2, we are going to swoop. Why are we swooping? Because it is even. At 5, we're going to go through because it is odd. And at 9, we're going to go swoop because 30 is even. And we're going to go, why did you write that right here when it should have been over there? All right, the y-intercept is going to be a really, really big negative number. And I have placed it perfectly because once I figure that out, I would write it right there. All right, you try it. Go ahead and give me a quick sketch of this one, and I'll pause for a second. boom, I'm back. Hopefully you got something like this. So Desmos is an amazing program. Allows us to put any graph we want, reshape it. Notice that on this one I picked A for our leading coefficient, and then I got to pick M, N, and P. So far, that's certainly what it should be. Notice what happens when I pick A to change. A is still positive, positive. So yeah, those little bumps in between and the steepness everywhere changes. So that makes a lot of sense. If I go negative, yep, the N behavior flips. And it's pretty cool. It's pretty cool. So if we leave that maybe on 2, look what happens when I picked M, N, and P as integers. So when I bump this, it's going to go to 2. Notice M is over the 1, so if it's even, it swoops now. It swoops. So this is a great way to kind of mess around and make sure you feel pretty good about this. They're all even. Got a positive A value. We're going to swoop at all of those. What if we make this one even, but a little higher power? It's going to smush it down just a little bit. Pretty cool. So you can mess around with this. I've included this Desmos for you to mess around with. That's for me. All right, so let's say we have a graph and we've got to work backwards. Everything's super easy except the A value. And that's where that y-intercept, or any point on the graph, any point on the graph. All right, so if I were to do this one, I want to note that point, and that point. So x plus 1, x minus 2, and x minus 3. Piece of cake. If we didn't know this was a cubic, then I could make these exponents any number I want as long as they're odd or even, depending on what's happening in the graph. This would make that exponent have to be odd, odd, and odd. Since it's cubic, we know they all have to be 1. Boring, but that's the way it is. So we're done, sort of. We have to put an A there. That A is going to now allow us to stretch it up and down no matter where we are. A lot of times they give you the y-intercept, but that doesn't matter. They could give you maybe this point, just as long as they give you an x and a y, because this point here is really an x and a y. All right, so we plug in 0 for x, 12 for y. And we get A is equal to positive 6, positive 2. All right, that is the specific cubic. All right, on this picture over here, why don't you try it real quick and pause it. Boom. And now we're back. So hopefully you wrote something like this. The first one is x plus 2. X plus 1, and x minus 2. Now I have to decide about the exponents, odd, odd, even. Really, since this has to be a quartic, my hands are tied a little bit. That has to be a 1, and this has to be an even, so that has to be a 2. That's it. Oh, we got to figure out what A is. So we're going to plug in the point 0, negative 16. So negative 16 equals A times 2 times 1 times negative 2 squared. Whoa! Don't forget the squared. Don't forget the squared. So that's 4, 8. Divide by 8. We get negative 2 equals A. Not too tough. I think you can handle it. Come on. Give yourself a little vote of confidence there. All right. So now, how are we going to mess with you a little bit? Maybe we'll give you a polynomial and a little bit about it, so you got to use your techniques to figure out how to rewrite this. All right. We have some skills, ladies and gentlemen. We just haven't had to use them yet. So I love that I don't know why this. All right. Given 1 is a 0 of that polynomial, fully factorized. All right. So if 1 is a 0, that means x minus 1 is a factor. That means I can rewrite that polynomial as x minus 1 times something equals that polynomial. Well, how do you pull those factors out? My good friend synthetic division is my choice. So remember, you take the coefficients, and if there's like a term missing, like an x to the fourth or an x to the first, whatever, you got to put a 0 placeholder. So 3, 2, 1. So we have them all. So now we do synthetic division. -2, -2, -4, -4, 6, and 6. We get 0. Great way to check your work. If they say it's a factor or a 0, you got to get 0 there. So remember, this is the coefficients of our resulting polynomial. So p of x can now be written as x minus 1 times -2x squared minus 4x plus 6. Your job now is to deal with that quadratic. And man, I would pull out a -2. All right, so you're like, oh, I'll factor. Wait a minute. This doesn't really factor right. So what do? You go back and check all your work, because how dare I give you a problem that doesn't factor. But that's what you need to get used to. So how do you deal with quadratics that don't factor right? Well, you use the quadratic formula, which always works. So -4 plus or minus the square root b squared minus 4 times a times c all over 2a, and that's going to give me -4 plus or minus square root of, I think 28 over 2. You know, we could leave it like that, but I know 28 is 4 times 7. I know the square root of 4 is 2, so I get -4 plus or minus 2 times the square root of 7 over 2. 2 goes into both of those, so -2 plus or minus the square root of 7. All right, that is an answer that your technology is not going to give you. But I guarantee you on the IB exams, they're going to want to know exact values. All right, so all we're doing, ladies and gentlemen, is putting our skills together. So I think this problem asks for, hence sketch the graph. All right, describe the behavior of the graph. All right, so we know this is let's do it right here. We have a negative odd. So that is going to be something goes here and here. We know we have a root at 1. And we have roots at -2 plus or minus the square root of 7. Where are those? Well, I know that square root of 7's got to be between 2 and 3. So the first one's got to be around here, and the second one's got to be equidistant. So I'm going to say here. So we say -2. Man, I got it. All right, so 4, 9. I got to figure out what, because this point right here, that may be in between. So let me check that out real quick. All right, a little bit of work. I just found out this point is really, I love them. I think it's like that because square root of 7 is 2.6, so that's got to be like 0.6. Got to be careful. Wow. All right, so this is plus square root of 7, -2 minus square root of 7. All right, so here we go. Boom, boom, something like that. All right. All right, so using technology to rewrite in factored form. So sometimes they don't give you the clue, so you're going to have to just plug this stuff into the equation. When you're given something kind of messy like this, just rewrite it as all on one side and equal to 0. So I'd say that my polynomial is equal to 2x to the fourth minus 13x cubed plus 27x squared minus 13x minus 15. All right, as you can see, I have plugged this in, and I have found using technology that it crosses at -1/2 and 3. What if those are decimals? Well, I got an example of that for you later. So here you are. What I'm going to do is I'm going to factor out the x minus 3. And later on, I'm going to factor out the x plus 1/2. And as I do that, I'm going to be left with the function. And if I pull out two linears out of a quartic, I should have a quadratic. That's something I can deal with. All right, let's see if it works. So 2, 6, -7, -21, 6, 18, 5, 15. Bams skis. All right. Well, here's a little cool thing. If I know that I am now about to pull this factor out, I can just do synthetic division on the resulting polynomial. So this is going to be -1/2. Let's see if it works. 2, I get -1, -8, 4, 10, -5. Yeah, baby! So this is going to be 2x squared minus 8x plus 10, which is 2 times x squared minus 4x plus 5 equal to 0. Mr. Sayers, are you kidding me? Does this factor? Well, yeah, x minus x. Oh, yes, we have the quadratic formula, thank goodness. Minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. 4 plus or minus the square root of -4 over 2. This is getting exciting. 2 plus or minus 2i over 2. And finally, we have zeros at 1 plus or minus I. That makes a lot of sense. Why, Mr. Sayers? Because let's go back up and look at the graph. We expect 4 roots to a 4th degree polynomial. That's actually the next section, or the section, oh, it was the section before. So, but we are only given this one and this one, so we're kind of expecting 2 roots that are complex conjugates that don't show up crossing the x-axis. Bam! That is beautiful. All right, inequalities. Last thing, I know we're pushing it, but we're going to push it anyways. If I ask you where the polynomial is greater than 0, just look at the graph. We've worked this hard to get the graphs. It looks like to me that it is greater than 0 for this interval and greater than 0 for this interval. Yes, there's no like algebra here. Just look. Where is the graph above the x-axis? So we would say something crazy like interval notation. That wouldn't be. Remember that, where x is between, so we'd say x is an element of this interval, so from 1 to 2 exclusive, the brackets are facing out, meaning we don't include 2. Union is or, x is greater than 3, so that interval would look like 3, comma, infinity, and we never can include infinity, so been a while, huh? All right, you're welcome. All right, so let's do one example. We're walking along, we think we got it, and then they give us a problem that looks like this. This is just like, what? I don't even know where to start. Well, take a deep breath and get it all on one side. Okay, that's not too tough. Graph it, because they're not telling us any kind of cool things about it. So we graph it on Desmos, or actually you're going to have to make sure you can do this on your graphing calculator. And there's that polynomial. And we want to know when it's greater than, When is it less than or equal to 0? So I hope you can see that it's going to be that interval and that interval. If the problem only asks you for the estimate and you have technology, you can use these numbers. I wouldn't rely on it. I would rely on the idea that you're going to have to use your tools to find out those values exactly. So what would that look like? We know this one. We know that 1/2 is a root. So I would have 1/2 and I would do synthetic division on 2, -9, 2, 1. We know this is 0. If it is not 0, that's where you hit pause, figure out what you did wrong, and redo it. But I'm hoping. So 2, 1, -8, -4, -2, -1. Bamskis, feeling the love. What's the resulting? I'm going to factor out the 2 right away. So I get x squared minus 4x minus 1. Am I scared of that by now? No! That's just quadratic formula. So now I'm going to use quadratic formula, minus b plus or minus the square root b squared minus 4 times a times c all over 2a. So that's 4 plus or minus the square root of 20 over 2. That's 4 plus or minus 4 times 5, 2 times the square root of 5 over 2, which is 2 plus or minus the square root of 5. So I want to check my work. Plug in 2 plus the square root of 5. I better get 4.236. I'll bet I do. You've got this. You've got this. You've got this. There it is. That's fun when you've got this and you're rolling and you're like, bam. So have fun. Thanks for playing. We'll see you next time.